Good morning, class. Welcome to the online classes for class 12. In the previous classes, we were learning about the chapter moving charges and magnetism. In the last session, you have seen the topics toroid and the solenoid and the magnetic field at some point due to the toroid and the solenoid. You have seen by using the Ampere circuital law that we have found the magnetic field. Due to that, current Ampere circuits wounded around the solenoid or the ring, that is the toroid. So after that, there are some few small topics which you can see here. After that, the last topic of this chapter is there, which is Galvanometer, and next session we will be completing it, and after that we will be starting the new chapter, that is magnetism and matter. Sorry if there is disturbance due to my voice. Okay, just try to understand the topic. Here the first topic, that is work done by a magnetic force on a charged particle, is zero. What does it mean? We know that whenever a charged particle is allowed to move, then when moving charges possess electric field as well as a magnetic field, right? And if we talk about the magnetic force, then it is the force with how much it is magnetized, right? How much it is magnetized, and the magnetic field is denoted by the letter B. And since the particle is moving, so it is denoted by the letter, that is the velocity of the particle is moving, so the velocity of the particle is given by v, and the force experienced by the particle is given by F. So the magnetic force on that body due to the magnetic field is given by F Q V cross B. This we have seen in the first topic of our chapter, that what is the magnetic force. So we know that whenever this moves, we know by the Fleming's left hand or the right hand rule that the current, magnetic field and the force acting on that particle is always perpendicular to each other. So we know that this force always acts perpendicular to the velocity or the direction of the motion of the charge. Therefore, we can write that this force into velocity, that is velocity or the direction of the motion of the charge, is equals to the magnetic force, that is force into velocity. And keeping this dot product together, we can write it as 0, right? So force into velocity will be 0. But according to Newton's second law, we know that the force is directly proportional to the change in the rate of momentum with respect to the time, which is equals to mass into acceleration. So acceleration is the rate of change of velocity with respect to time. So it is m dv by dt. So again this mass, velocity and perpendicular to the direction of the v, so it will be d by dv by dt into v, so it is equals to 0. So on multiplying this, we know the multiplication of the differentiation, that is the product rule for the differentiation. So this is given by the m by 2 dv by dt into v plus v into dv by dt, and this d by dt is given as v into v, that is v square, and after the bracket closed, it is given as m by 2, and that m by 2, if it come inside, then it is d by dt of half mv square. And what this mv square tells us about, that is the energy of kinetic energy. So d by dt of kinetic energy is 0. So we can say here that the magnetic force that applied on the moving charge is 0, that is, does not change the kinetic energy of the charged particle. What does it mean? That whenever the charge is moving, the magnetic force does not apply any kind of the energy on it. So the charged particle moves with a constant velocity. And the work done on the charged particle by the magnetic force due to the magnetic field is 0. Similarly, motion of a charged particle in uniform magnetic field. Now, if the uniform magnetic field is present, that is inward or the outward direction, then it is given by the magnetic force due to the magnetic field B is given as F Q V B. Since it is a cross of the vectors, so it is given as QVB sin theta. Similarly, there are 3 cases possible for a moving charge in the uniform magnetic field, that the initial velocity is parallel to the magnetic field, and we know that the parallel magnetic field does not exert any force on the moving charged particle. They should be perpendicular to each other. So here, when the initial velocity is parallel, then it is 0, that is theta equals to 0 degree, then sin 0 is 0. So whenever the charged particle moves in the parallel direction, or the velocity of the particle is parallel to the magnetic field, and the magnetic field does not act on the particle. Next, when the initial velocity is perpendicular, that is theta equals to 90 degree, and we know that for the theta equals to 90 degree, or the motion of the charge of the particle is perpendicular to the magnetic field, then the magnetic force is high maximum, that is sine 90 is 1. So we can say here that the particles acting magnetic force is maximum. So for theta equals to 90 degrees, sine 90 it is 1, and QVP, that is the maximum force. So magnetic force on the particle perpendicular to the velocity, so it does not do any work, but it does not changes the velocity of the particle, but it will move with a uniform velocity. So this is the reason for the initial velocity is perpendicular to the magnetic field gives the maximum force. Here if you see the positive charged particles moving in the magnetic field directed into the plane of the paper. Here see small cross are made, and we have learned that whenever the magnetic field is moved inwards, then the inward direction towards the plane of the paper, if you think it is inward, then it is shown by the cross one. So this is a cross, and it is acts as a force, that is F is equals to QVB. So the force continuously deflects the particle without changing its speed. So it deflects because FQVB is there, so they will get deflected, but since it is moving in the circular loop, so some force is acting on it. So what it deflected with? It is deflected with some force towards the center, and that centered force is said to be the centripetal force. So we know that the magnetic force provides the centripetal force on that charge. So the speed does not changes, but it provides the force towards the center. And if you take it as moving in a circular path, then let the radius be r, and since the force acting on it towards the center, so it is given by mv square by r, which will be equal, so the force acting towards the center on that particle will be equal to the magnetic force, because it does not change the speed of the particle, it just let it move in the uniform velocity, so which will be equals to mv square by r, that is centripetal force, and the magnetic force is given by QVB sin theta, but sin theta is 90, so it will be QVB. So value of R will be mv upon QB. So they can say that the radius of circular orbit is inversely proportional to the charge, that is Q by m, and to the magnetic field. Okay, so what is the revolution time period for it? We know that time period is inversely proportional to nu, and circumference will be taken because the particle is moving around a circular path on the boundary, so it will be complete distance covered by that particle will be equal to the circumference of the circle, so it will be 2 pi r, and 2 pi r upon nu. Now here r's value is already taken by the centripetal force, which is mv upon qb, so on putting this value we got 2 pi m upon q, as v and v is taken as cancelled. So here this is the revolution for the time period for taking the revolution of the charged particle in the uniform magnetic field. If we take out the frequency, we know that they are both are inversely proportional to each other, so f is equals to 1 by t. So from here we can find qb upon 2 by m. This frequency is similar to that of the cyclotron frequency. We will see what the cyclotron is, but this is omitted part for your syllabus. You just have to read what is cyclotron to know, that's it. So after that, when initial velocity makes an arbitrary angle with the field direction. So whenever it makes an angle, we know that whenever the arbitrary angle means it is projected with an angle. So the uniform magnetic field B is set up along the x-axis. Here you can see that the helical shape is there, and the x-axis the magnetic field is working. So particle of charge q and mass m enters the magnetic field with velocity v and inclined at an angle theta with the direction of magnetic field. With the direction of magnetic field, it is inclined an angle with theta. So we can say that the velocity of the particle is along the, if you take its horizontal, and it is perpendicular to the magnetic field, and the motion of the charge is also perpendicular to the both. So we know that QVB, three of them are acting perpendicular to each other. So let us resolve that velocity into its vertical and the horizontal component. So one is v cos theta, and the vertical component is given by v sin theta. But we know that the circular path along the yz plane, it is moving in the yz plane. See, it is in the y and the above, and then down it will be z. So it is moving in the yz plane. Then r is equals to mv upon qb. We have know that but the velocity will be in the particular direction, right, which is to the top and the bottom, so it will be perpendicular to the magnetic field. So the only component working will be the vertical component, that is mv sine theta upon q. Okay, so now we have to find the time period for the revolution. We know that it is 2 pi r upon v. So 2 pi upon v, perpendicular will be used, so 2 pi v sine theta, and the formula for the r. So when we take this, the value of the time period is 2 pi m upon q. Okay, so thus the charged particle in the uniform magnetic field has two concurrent motion, that is linear motion along the x-axis and the circular motion in the plane, that is yz plane. So the resultant is in the form of the helix, right? So if it makes an angle, then it will move with an helical shape along the axis of direction of the magnetic field B. So the linear path distance traveled by the charged particle in the direction of the magnetic field during its period of revolution is known as the pitch, that is the highest maximum height or the maximum distance traveled by the charged particle. So it is given by the v cos theta because it is moving to the x-axis, and we are asking about the pitch, and the distance covered will be in the horizontal direction. So we will be taking the horizontal component of the v. So it is given by v cos theta into 2 pi m upon qb. So it is given by 2 pi mv cos theta upon qb. Okay, so this is the relation for the helical path. So the distance covered by the particle in the helical path is said to be the pitch. This is the formula for the pitch of the helical path. Here the motion of a charged particle in the perpendicular magnetic and the electric field. This is said to be the velocity selector also, because whenever the beam of the electron is passed through the two deflecting plates, here you can see one on the above, that is S1, and the second one is S2. So whenever these electrons are allowed to move between this particular electric and the magnetic field working in the perpendicular direction, then the electric field E acts in the downward direction. Here you can see the electric field lines in the downward direction. Then the electrons will deflect to the upward direction, because the electrons moves in the direction opposite to the direction of electric field. So here the electrons will move in the upward direction. And since the B is acting here in the normal direction to the plane of the paper, because cross is given, so it is acting as a perpendicular to the plane of the paper, that is inward direction. So the direction of the magnetic field is in the inward. So the deflects the electron in the downward directions. So here the electrons, both of them are just reflected downward direction. So here the two slits are kept, that is S1 and S2. So the electrons which are undeflected are passes through the S2, because if deflection is there on the particles, and they will try to move from one slit to the other slit, so there will be some deflection, that is they are start moving. So on this deflection, the electrons cannot move to the slit 2. So there are some undeflected electrons will pass through the slit 2, in which the magnetic force and the electric forces are opposite, right? Because if they act opposite and equal, then the electrons will remain undeflected, and they will try to move through the slit second slit, that is S2. So since the electric field and the magnetic field are acting on that, so they try to deflect the particle, but if they are at some point, if they are equal and opposite in direction, so they will be cancel each other, and the particle will remain undeflected, which will pass through the slit 2. So the velocity of that undeflected particle will be equals to the, when this undeflected part is there, when the undeflected particle is due to the equal and the opposite magnetic as well as electric force. The electric force is given by the product of the charge on that electron, and similarly for the magnetic force we know QVB sin theta. Same from here, the Q will be given by E, that is electron. So E and the electric field, that is a charge on the electron due to the electric field E, and the capital E is for electric field, is equals to EVB, where the charge of the particle, that is electron. So what magnetic force is working on it due to the magnetic field. So E is equals to EVB. From here we will find the velocity, that is electric field upon magnetic field. So we can say that whenever the charged particles are present inside the particular velocity, moving with the velocity between the electric field and the magnetic field that acts in the same direction, then the electrons are said to be with some particular velocity remain undeflected and can be come to the slit second. So we can say that the electron with a particular velocity can be selected from here. So this arrangement is done to select the particles of a particular velocity. So this is said to be the velocity selector. So velocity select, or the velocity filter is also the same. So here are the formulas which we have seen, that the electric force is given by QE, magnetic force is given by QEB sin theta. If it is parallel, then it is a minimum magnetic force acting on the particle. If it is perpendicular, then sin 90 it is a maximum magnetic force acting on the particle. And we know that whenever the particles try to move in the circular path, then it will be centripetal force acting on the particle to move in the circle path with the force acting towards the center, which is equal to centripetal force, and it is given by mv square by r, which will be equal to the magnetic force acting on that particle, that is qvb equals to mv square by r. From here the value of r will be mv upon qb. So if you have to find the time period of the particle to move in a circular path, will be equals to 2 pi upon u, which is equals to 2 pi m upon qb. Similarly, the t and the frequency are inversely proportional to each other, so frequency equals to qb upon 2 pi m. Now when the particle moving with the velocity v and it makes an angle with the magnetic field B, then we have seen that it moves in the helical path. It makes a helical path. From here, if we see the value of the radius for that particle will be equals to mv sin theta upon qb, because it is the only direction of the perpendicular will be working on it. So vertical direction will be given as mv sin theta upon qb, because we have resolved that to the horizontal and the vertical component of the velocity. So in the helical path it is moving in the yz plane, right? It is rotating in the yz plane to the magnetic field. So we can say that here mv sin theta upon qb. So time period is equal to 2 pi m upon qb. And if we talk about the phase, that is the distance covered by the particle which is along the magnetic field direction, that is along the x-axis. So here it will depend on the horizontal direction, that is v cos theta. So v cos theta is equals to, so if you have to find the time period, then it is equals to 2 pi m v cos theta upon qb. Okay, so when it is electrons are tried to accelerate, then it is given by the kinetic energy will be always equal to the velocity with which it is moving. So both are equal. So for here we can find the velocity of the particle. Okay, so here are some numericals which you can see. An electron moving horizontally with the velocity is moving in the horizontal direction. So here it will be moving in the horizontal direction with in the region of the uniform magnetic field of 10 to the power minus 5 Tesla. That is the value of B is given. Vertically downwards 3 is acting. So perpendicular direction is given for the magnetic field which is acting vertically downwards. So draw its trajectory and find out how much time it to come out from the region of the magnetic field. So we have to take out the time and have to tell the path with which it travel and how much time will it take to come out from the region of the magnetic field. So since the vertically downward direction is shown, so it is given as that the electron moves along a semicircular trajectory inside the magnetic field, because whenever the inside particle, that is the magnetic field, is inside the inward direction, so we have to take the right hand rule and see whether the magnetic field is showing it is in the circular loop, so the electron will move in the circular path. So the trajectory is in the circular path, and we know that for the circular path the electrons will get a force towards the center which is given by the centripetal force, which is equals to mv square by r, and it will equals to the magnetic force, that is qvb. So on putting the values, that q is 1.6, the charge on the electron will be given as 1.6 into 10 to the power minus 19, and the mass of the electron is given by 9.1 into 10 to the power minus 31, and here the velocity is given as 4 into 10 to the power 4, and the b is given as 10 to the power minus 5 Tesla. So on putting this value, we can find the value of the distance, that is the travel radius r for the path through which it can travel through the circular orbit. So what is it now? We have to find out what is the time taken by the body. Time taken is given by 2 pi upon u, but since it is moving in a semicircular, so it will be equals to pi r upon u. So it is moving along a semicircular part inside the magnetic field and comes out as shown in the figure. So here it will be moving in a circular path, but in the semicircle, so it will be given by pi r. So value of pi and r is kept here, and u is given by 7 into 4. 7 came from the value of the pi, okay, it does not come from the velocity, because velocity value was 4 into 10 to the power 4 meter per second. Now next question, that an electron travels in a circular path of radius 20 cm in the magnetic field. So the b value is given. We have to find the speed of the electron. We know that to find the speed of the electron moves moving in the circular path. So the centripetal force will be acting on it, that is QVV should be equals to the mv square by r. From here we can find the velocity, that is v is equals to e dr upon EBR upon m. From here, magnetic field is given as 2 into 10 to the power minus 3 Tesla. Electron's charge is given as 1.6 into 10 to the power minus 19. And the radius, that is the distance, is given by 20 into 10 to the power minus 2 meter, because it is kept at the radius of 20 centimeters. So we have converted it into meter. So here the value of the velocity is given by 7 into 10 to the power minus 7 meter per second. And if we have to find second, that is what is the potential difference through which the electron must be accelerated. So it is a potential difference. We can write that the half mv square will be equals to the force experienced by the charged particle due to the electric field. So it is given by the electric field will be given by the potential difference v. So EV is equals to half mv square. So from here we can find out the volumes, that is voltage, that is V, potential difference. So on finding this value we got it as 14 kilovolts. Okay, here the torque experienced by the current loop in a uniform magnetic field. So if we keep a current loop in the uniform magnetic field, so here you can see the two magnets are kept with the poles north and the south pole. So both the pole will try to move this uniform magnetic field, the current loop will try to move in the both the directions, because some two forces will be acting on it. One of them will try to move it in the direction of the magnetic field, another will move in the opposing the direction of the magnetic field. So here the two forces, that is a couple of forces, are acting on this current loop, which is equals to the torque, which is given by the torque. So in the down figure you can see that from the top view we can see that one force is try to moving in the upward direction, that is try to moving in the upward, and another one will moving in the downward. So some couple of forces are trying to move it. So here we can say that the torque is working, and this torque working will be depending on what the coil is made of, that is how many current, what is the current flowing through the coil, and what is the area of the coil, and what the angle is made between the particles magnetic field and the mass of that particle. So we can say that the angle between the B and the normal to the plane. So how it will be given as, we know that the torque is given by the force into the perpendicular distance between them. Now what is the force here? It will be given as I, that is the current acting on it, and the B, which is the area of the loop, that is the length of the loop, and capital V is the magnetic field. So it is equals to I small b into capital B, and the perpendicular distance, since the distance is A, but for the horizontal it is A cos theta, and for the vertical it is A sin theta. So it is given as I B A sin theta. Okay, so it is value of the torque. But if we take the number of turns of that loop will be capital N, then it is going to be given by N I B A sin theta. We know the magnetic moment here, the magnetic moment was given by the angle theta, which is made with an angle theta with the magnetic field B. So it will be equals to torque equals to mb sin theta, where B is magnetic field, M is the magnetic moment. So it is equals to torque is equals to M cross B, that is magnetic moment and the magnetic field. So both the forces just try to make it in the revolution, right? So they try to move. So the couple of forces is given by N I B A and M cross B. So this was the relation, that is the torque working on the loop of any shape it is, but it will working on the same. So these are the small topics around the chapter. After that we have to find the galvanometer, because I have to read it. It is an important topic, that what is galvanometer, its working, and how we can convert that into the ammeter and the voltmeter. That is the last topic for your chapter, because cyclotron is deleted. We will be seeing what that cyclotron is, but the topic is deleted for your numericals and the concept. So thank you class.